everyone. These are the ones that are showing true grit, the ones that are left. So you deserve an applause yourself. As you can see, I'm going to talk sort of about Innosen. My presentation today consists broadly of two parts. The first part is a bit of theory. The next part, I'm going to talk about some of our products and how the theory that I will have taught you before applies to the products. We've got a holding. Innosen now exists around 7 years. It was a spin-off out of Syncom. Our holding is in Hong Kong. We have operating companies in Spain and in the Philippines. This was already told, so I'll skip that. As you can see in the program, I'm going to talk about step-by-step sort of process improvement. The first thing that, of course, you will do is give you an introduction. First, what I'm doing here, then the basics about process improvement. Then I'll talk briefly about fault mode and effect analysis, examples, and we'll then come to the conclusion. These are the questions that whenever you embark on anything, you should ask yourself, why should you do it in the first place? And once you've decided that you're going to do it, that it's a good idea, what exactly are you going to do? Because there might be many options that you could choose for. And which one are you going to pick? And once you've decided what it is that you're going to do, how are you going to go about it? So first, the why. Well, as always in business and the world of the grown-ups, it's all about money. So if we sort of talk about step-by-step process improvement, that's only interesting if that improvement actually, at the end of the day, is going to make us more money. It's all about return on investment. Now, I'm going to talk mainly about three pieces, as I said. When you start on a project, could be a small project, could be a complete can line, what you always do is you start with a business plan. And in that business plan, you make a number of assumptions. When all the assumptions come true, you will end up with a certain rate of return. And that's what I'm showing here on this graph. I'll explain. Oh, sorry, I'm going too fast, pressing the wrong button. I wanted the laser. Here we are. So what you see here is the 0 point. These are deviations from an assumption that you would have made. What you see on the vertical axis is the rate of return. Over here, you see names of certain variables I made assumptions for. I made an assumption for material cost. I made an assumption for the number of people I would need to run my operation. I made an assumption for the amount of factory floor space that I needed. And also an assumption for the number of cans that I would be able to produce if I actually made this investment. Now, of course, assumptions are just that. They're assumptions. You try your best, but you never know that you get it 100% right. So what you do is you make this sensitivity analysis. So what you do now, and this is all part before you ever spend a penny, you assume that, for example, and I'll just take sort of people as an example, you start the operation and it appears you can't do it with the number of people you thought. You need like 10% more. But if you need 10% more people, that means you have higher costs. Your rate of return is no longer the 15%, but it's just dropped to 10%. If you need more floor space, you can see more floor space in my model has hardly got an effect. Need a few square meters extra, don't get sort of hung up on it, just do it. The ones that are of particular concern are the ones that have very steep lines, like, for example, production, like, for example, material cost. Well, we all know that material cost is about 80% of our cost, so if the material cost goes up, you sort of see your profitability dropping very, very, very rapidly. Again, these are just assumptions I've made. This is not an accurate graph, so you'll have to do your own homework. But sort of in general, it absolutely holds true that, for example, if your production sort of goes up, your rate of return on your investment skyrockets. Conversely, if you do not make as many cans as you thought, all of a sudden your investment turns out to be a very bad investment. So in other words, making the right number of cans is one of the most important things. Now, making of cans is not just about quantity, it's also about quality, because you need to be able to sell your cans. If you produce scrap, those are the most expensive products you could probably make, because you spent all the material, you spent all the labor, you spent all the electricity, and then you have to throw it in the trash can. Yeah, so when I talk about production, this is production of commercial quality cans, cans that you can sell, that your brand owners are willing to give you money for. So you need to try and maximize that. That is one of the, because the material cost is not a very steep one. Yeah, you depend on your negotiators, but there's not really a lot that you can do in the day-to-day operation. So I already said this, it's about quality and it's about quantity. Both are equally important. So now we've established that what we really need is as large a number of cans as we can possibly get out of our investment. The question is, how are we going to go about it? How do we do it? Any process that you need to sort of improve will appear to be hard. One of the speakers has said this before, there is no revolution, there is just evolution. If there would be sort of a simple trick, somebody would have done it 50 years ago. It's going to be a matter of grit, and that's something that you all appear to be good at, so I'm sure that you'll manage this as well. Let's look at the process and how you do it. Anything that you want to improve, you need to, first of all, establish your starting point. Where are you? Once you've established your starting point, you can start to make changes in the process. And then when you then measure again, you can see whether you've actually moved forward or backward. So then you can see whether you've made progress. So it's always a matter of measuring, comparing with your target, and then making corrections, and then starting again. In process terms, it would look like this. You have products sort of going into a process, product comes out of the process, and some operation takes place here. You take samples, or you measure everything. In this block, you compare it with what it should be, and if it's not right, you go back, make adjustments to the process, and the process, sort of the cycle, repeats itself. And every time, you hope you get closer to that desired value that you needed for that particular parameter. Crucial in all of this is the measurement. I'm emphasizing that, it was already sort of emphasized by my colleagues of Sencon. The most important thing about the measurement is, can you actually trust it? Because you are going to base your decisions on it. If I go back to this, we took the measurement, we compared it with the value, and then we started changing things. Now, just imagine that that measurement that you took is not reliable, that you cannot trust it. You might actually make the wrong adjustments to your process. And I have a very interesting example about this. We were heavily involved sort of in film measurement of coating lines. And one of our customers had a huge problem with big coating sort of thickness variations. The first thing they did is just introduce a logbook, a very simple thing, put it next to the coating line and told the operators, every time you make an adjustment, we want you to write in the logbook why you actually did it. Well, it seems simple enough. After they'd been going for a few months and started analyzing the data, what struck them was that every time when there was a shift change, the process had to be changed. So in other words, every time, 10 o'clock, because that's when their shift change was, 10 o'clock in the evening, somebody would start changing to the coating line. And you think, how on earth is this possible? Now what happened when you analyze it further, the guy that was running the coater, he felt really responsible, and he wanted to make sure that everything would be all right for his colleague when he arrived. So just before the end of his shift, he would take a sheet, he would measure it, and everything was absolutely perfect, and he was happy, he would go home. Then the colleague comes. First thing, he's now responsible, so first thing he does, he takes a sheet, he measures it, guess what? Wrong again. Every time wrong. Well, that's of course not very logical. It's not, sort of the coating machine doesn't know that there is a shift change. So it should not always change sort of when sort of the shift changes. This was an example of a gauge that they used to measure the sheets with that was not very reliable. When sort of one person measured, it was okay. When the second person, a few minutes later, measures, it was always wrong. Now, to determine whether your gauges are acceptable for the process that you're trying to control, the industry standard is now the repeatability and reproducibility process. What is that? In very simple terms, you assume that every measurement system has two errors. One error is caused by the equipment itself, by the gauge itself. The other error is caused by the operator. There is a method to separately determine how big these errors are. So you will determine the operator variation, the operator error, and you will determine the gauge, the measurement equipment error. Then there's a statistical method on how to add these two together, and then you have the total error for your measurement system. What you now do is you compare that error that you've got with your measurement system with the precision by which you want to control your process. So for example, in coating terms, just imagine that my total error is, say, 2 grams per square meter, but I want to control my process to 1 gram per square meter. It's quite understandable, I'll never get there. I cannot control a 1 gram process with a gauge that has a 2 gram fault. So R&R is a percentage, and it expresses the total error of the gauge as how accurate you want to control your process. So a gauge that's perfectly suitable for one process, that for example has a big tolerance, might not be suitable to control another process that has sort of a much smaller process. So the first thing is you determine the R&R. We'll skip this one. The process that I described was that you would measure, you take a sample, you measure, you make corrections, you start again. Now, that works, and that works quite well to a certain degree. But just imagine that your problem is with double sheets. It's your coating line. It results in sheets that are not sort of coated every now and then. You get customer complaints. Now you could, of course, start measuring, you could sort of make corrections on the process, you could perhaps have different spreading magnets, you could have higher blast air sort of that you have on the sheets, you might have different sizes sucker cups, you might control your vacuum better, you can do all those things, but you still, every now and then, are going to get a dull sheet. Now, you cannot keep on improving forever because the economy is not there. At a certain point, you just have to be happy that it's as good as it's going to get, and you'll have to give up. But that doesn't mean that you can tolerate these errors. So what you now need is what another speaker the previous day called a gatekeeper. You kind of need something to catch the outliers. This is typically what vision systems are used for. This is typically what sensors, specialized sensors, are used for. So instead of keeping on going forever and wasting your money trying to get the last 0.00% of faults out of your line, give up on it and invest your money in a gatekeeper, because the investment, return on that investment is actually going to be higher. So how does this fault mode and effect analysis work? And I have to apologize before I show you the sheet because I couldn't think of a better way to present it, but it's kind of a spreadsheet and it's too small. It's this. So, but I'll walk you through it and explain sort of what it is that we're trying to do here. You first of all choose a function that you want to sort of improve, and in this case it was all about the lacquering of the sheets and the fact that every now and then we would have one that would slip through that was not lacquered or not fully sort of lacquered. What you then do is you say, okay, what are the potentials if an unlacquered sheet goes through? What is the damage that it could cause? What is the potential effect of the failure? And that's the first factor that's important, how severe is that if it happens? So you grade that from 1 to 10. 10 being catastrophical, so this is pretty close to catastrophical because If you have an unlacquered sheet, you may cancel it and kick it to your customers, they're not going to be happy. The next thing is that you then start looking for all the potential reasons why you could have an unlacquered sheet. You could have, somebody could have forgotten to fill up your lacquer tank. You might not have a double sheet detector sort of fitted. The double sheet could have perhaps not been corrected, sort of adjusted correctly. So there's a load of things that could cause it. And what you do is you then say, okay, you sort of give a number to the number, how often that actually occurs. So if it's something that occurs a lot, you would sort of give it a 10. If it's something that only happens very seldom, you give it a lower number. So you now have how severe it is and how often it happens. And the third one that you try to give a number to is, can you actually detect it? How easy is it to find it? And if it's a severe problem but it's easy to find, then it's not so bad after all. Yeah, so what you do is you multiply sort of how severe it is, how often it occurs, times how easy it is to detect. And then you get just a numerical value. And this numerical value, the higher it is, the higher your priority should be to try and crack that problem. So this is kind of when we said, okay, what should we be working on? This will hopefully give you a clue of where you should sort of spend your attention and your time. It's not always a matter of equipment. It can also be a matter of education. It could be a matter of discipline. There's all sorts of soft things that sort of come into play as well, and those are actually the most difficult ones, because what I absolutely hate is when you ask somebody why you're doing it like this, oh, we've always done it like that. Well, that is not a very good reason. I mean, wrong is wrong. It doesn't matter if everybody is doing it. And right is right. Something that is correct is always correct, even if nobody is doing it. But it's hard to convince the people in the factories. You have this human inertia that can absolutely sort of stifle progress. So it's not easy. You can analyze it, but it's not easy to actually get it done, and it requires a lot of convincing from your end. So I've already sort of spoken about this. First of all, measure, compare with the standard, make the correction in the process. If you can't do that, go for the gatekeepers. I'm now going to go and explain some of the products that we've got. Some of them are gatekeepers, some are the ones that you would use for measurement, some are combo products, I would say. They do a bit of both. Double sheet. Everybody here would probably use double sheets. And you would wonder and say, why on earth did you even develop one? Because there are so many on the market, why bother? Well, we were actually asked by one of the world's biggest can makers to make one. Why? And this is part of the fault code and effect analysis. They work brilliantly if you adjust them. But if you forget to adjust them, or if you adjust them wrongly, you might as well not even have one. So what they wanted was one that you could not adjust. No push buttons that you could forget to push, no potentiometers that you had to turn. They just wanted one that you could fit and that you would never touch, and it would just work. So that's what we developed. So this one solves that particular issue. Look, some people in this room are actually using sort of this one. It's, I would say, virtually the standard for all the big can makers sort of in the world. Missing lacquer detectors. I told you about missing lacquer. This is a gatekeeper sensor. You can install it in two places. You can install it sort of on the lacquering line. If the sheet is stable enough, you can install it on the slitter. We have customers that install this sensor after the welder, after the cylinders have been formed. So that the cylinders come out with a high speed. Usually the lacquer is on the inside, nothing on the outside. Sometimes a blank flips, or somebody's measured a sheet, puts it on the stack the wrong way around, and all of a sudden you have cans with lacquer on the outside and nothing on the inside. Well, this sensor will actually detect those, even if it's totally clear varnishes that the operators can't see. It will just do it. I'm going to skip this one. This one, I would say, is a combo product. It's a gatekeeper, it's a measurement device at the same time. This is one fitted on the lacquering line that has a skew on the sheets going in. The term skew might not be clear for everyone. What it is when the sheets go into the lacquering line, you want them to be parallel with the side of the lacquering line, perpendicular to the lacquering roll. And if they turn, the margins later are not going to be in the right place. So the turning of the sheet is called the skew. So what this one does is for every single sheet, it measures the skew. And it gives you a numeric value on the display. It really measures it very, very accurately to about 20 microns. You can adjust what is acceptable for you. The moment that the value is too big, you will raise a signal. You'll either reject the sheet, stop the line, take it off, whatever you choose. But this also, because it measures, can be used to improve the process. It makes a standard deviation, it makes an average, and you, for example, if you normally have a standard deviation of 0.2 and you start it and you see it creeping up, it could be that the tension on your chains is sufficient, that your dogs are worn out, there's something wrong with your gripper cylinder. That is the kind of information that you will get from this system. We also have one that measures the sideway movement of the sheet, so if it doesn't twist but just misses the side lay, also camera-based. This is one that will do sort of the registration with the roll, important if you have spot codes, because you can measure if the spots are in the right position on the metal. Plane margin. This one does, again, it's a gatekeeper type sensor. If you have contamination in the margin, this is fitted on the splitter, it will just detect it so that you do not get your weld wires sort of burning, you don't have leaky cans. Coating thickness, we do this together with our friends from Sengkok. So we also have this hover probe. It was developed a long time ago, but it's still sort of going. I would say it still is the standard in the world. I'll immediately admit that sort of an optical filter gauge will probably give you, or does give you, sort of better and more accurate results. But they're so accurate that you possibly do not need them. It's a lot more expensive, and not everybody has the money sort of for that kind of equipment. This is quite affordable. Enamel rating, people have been enamel rating for donkey's years. We did sort of ourselves a fault sort of mode and effect analysis on the gauge. And we found that there were a number of issues. For example, the contact with the can. When the contact with the can is bad, you get fantastic readings, but in reality your cans could be crap, but you won't know. So we've changed the system, and we now check that the contact with the can is correct. Otherwise it won't even start measuring. We found that the electrodes, they're normally made of stainless steel, they get covered in rust. Well, that rust has a series resistance and actually affects your measurement. It comes out more favorable than it really is. So you think you're making good cans, but you're not. We sort of changed all that. We started using sort of titanium probes. They are inert as glass. They do not corrode. They virtually last forever. But it's just an example of a small sort of improvement on a gauge that probably every factory is using. UV logger. This is a measurement device. We were showing it sort of at the booth. This is a little measurement device. It is absolutely tiny. I have one here. Come and see me sort of at the booth. It's the size of a credit card, 6 millimeters thick. You stick it on a sheet, it's got magnets, you feed it through your UV oven, and it records both the intensity and the power sort of each of your lamps. You can just store that on a PC and compare it to what it should be. We have one that is a broad spectrum one. We are right now sort of sending out prototypes of one that will do UV A, B, and C together. Apart from the size, also the price is very important. It costs about a quarter of our sort of nearest competitor. So, conclusions. We're almost there. When it comes to process improvement, no shortcuts, no quick fixes, sheer graft. You need to keep at it. It's not necessarily easy. You need to make sure that when you use gauges, when you start measuring, that you can trust those gauges. If you can't trust them, you might as well not get started. So do your R&R trials before you embark on any process improvement. The process improvement sort of is kind of finite. You should only go so far, because if you overdo it, you're going to waste your money. Instead of overdoing it, install in the gatekeepers, install in the sensors that will take the statistical outliers out of production. So I think that's really all I wanted to tell you today. If you have more questions, we will still be around. My colleague Blessy is here at the front. We will be at the tabletop. We will be socializing. We'd love to help you with any questions you might have. I would like to thank you very much.